absolute continuity on curves. So recall that we say a function u defined on a metric space is absolutely continuous on a rectifiable curve gamma from a, b into x. And we will, without loss of generality, always assume that our curves are arc length parameterized. I may or may not forget to mention this explicitly each time, but you can, without loss of generality, always assume they are arc length parameterized. This is because any rectifiable curve, any Lipschitz curve, can be reparameterized to be arc length. We've discussed this extensively. So we say a function real valued is absolutely continuous on a curve if the composition u o gamma, which is now a map from interval into R, is absolutely continuous in the usual analysis slash calculus sense, because now we are in this familiar setting of an interval mapping into R. Also, these intervals for us are always compact, so we're not looking at half open intervals. Okay, so now let's put together what else we learned about absolute continuity. From the theorems that we have been discussing so far, it follows that there exists some g which is integrable on a b, and the function, the absolutely continuous function u gamma, is given as the integral of g, the fundamental theorem type equality holds, which in particular means that u gamma difference between two inputs is none other than absolute value, absolute value, I'm running ahead of myself. So this will be g, so u gamma will be absolutely continuous if it has a derivative, so g is nothing other than the derivative of u gamma integrated between t1 and t2. For every t1 and t2 in the interval, I want to work with the absolute value for the reasons that will be apparent soon. And once I take absolute value, I get an inequality if I put the absolute value inside. And this will go from t1 to t2. For every t1 and t2 in my interval. Okay, so let's keep it somewhere. So we have a function g. If u is absolutely continuous on gamma, we have a function g, so that integrating that controls the difference in the function values at the endpoints. Like here we're looking at gamma at t1 and then gamma at t2. So pictorially, let's also draw some pictures, they never hurt. So this is our metric space, can be anything. And then there is this path, which also can be quite wild, can have infinitely many self-intersections. Here I'm just doing one for the sake of illustration. So this is the curve gamma going from interval AB into space X, and there is the function u going into R, and here is the composition u composed with gamma, and the situation again, that integral tells us something. Now let's compare this to the situation in Rn, and in this case, let's say, okay, X is in Rn metric space, gamma is again an arc length parameterized C1 curve, and u from Rn, which is our X into R, is also C1. Then I've done this calculation once before, so I will be quite fast here. So UO gamma between two values, although this is multi-dimensional, this will indeed again be from the chain rule, gradient of U evaluated at gamma t multiplied with gamma prime of t, which is a vector. So this is dot product between t1 and t2. Again, if I put absolute values here, so the reason, for example, if gamma is a loop and at t1 and t2 comes back to the same value, then this side is 0, and this integral should end up being 0, which is possible only because this gamma prime keeps changing direction. And because in a general metric space we won't have such notion of direction and dot product to have really cancellation in the integral, we will always work with non-negative values basically. And that is why after this, again, we can put the absolute value in the inside and get an inequality. And then we have absolute value of dot product less than by Cauchy-Schwarz, the absolute value of the vectors involved. And absolute value of gamma prime is equal to 1 because gamma is arc length parameterized. Very similar formula to the one above, with GT playing the role of absolute value of gamma at t. But there is one very important difference, and that is that here absolute value of U is an object defined on the space X. So if I look at this as a function, absolute value defined from X into R, more specifically because it's never negative into this space, then integrating this along the path from the part of path from T1 to T2, by definition, this path integral is exactly the quantity here. And therefore, what I'm saying is that there is an object defined on the space, and its integral over a path dominates the difference in U values between the endpoints of that path. So this example and the previous one, in the previous one, this G is not really a function defined on the space, but there are things we can do. The first is that, well, I'm going to keep it simple. I don't want to discuss the more general case, but here, let's add this, that if gamma is injective, then setting this function rho of x, well, first of all, let me say this is a function again from the space X. I want to replace this extrinsic object. G is defined on AB, but I want to produce an intrinsic object defined on the metric space. So here I let rho be defined with this quantity, because G could be infinity at some points, I allow that, by setting this rho of a value is G of gamma t if gamma t is equal to x. So I go here, and I want to define the value of rho here. So this is a point x. Because it is on the curve and the curve is injective, there is a unique t which maps gamma under gamma to this x. And then g of t here is evaluated, so I basically just transfer or pull back or push forward, whichever way you want to think about it, the values of g onto the metric space. Injectivity here was used. So if I define it this way, then this integral here, again, is by definition integral of rho along the curve between T1 and T2. So now we have exact analogy in the two cases. So one of them, we started with a absolutely continuous function on a curve, and then we ended up, under the injectivity assumption of the curve, we ended up with something like this. Integrating a function on the x on the curve dominates the changes in values of u. And here we get it under any assumption. So here our rho is like this one. So, and these two examples should now motivate us to define the following. Let me consult my notes here as well. Okay, definition. We say a Borel function, rho from x to 0 infinity inclusive is an upper gradient of a function u from x into the extended real lines, so r, but also plus minus infinity. So we say that a Borel function is an upper gradient of u on or along, I use both these prepositions, so along a curve, again, arc length parameterized, a non-constant. We will actually exclude, for the reason that I will explain shortly, a constant path forever. So we never want to allow them in our analyses. So an arc length parameterized non-constant curve gamma from AB into X if for every T1 and T2 in this interval, the U at gamma of T2 minus U at gamma of T1 in absolute value is dominated by integrating rho along that part of the gamma, along this subcurve of gamma, ds. Okay. There are some caveat we have to take into account. It is understood that left-hand side is equal to plus infinity whenever one or both quantities, a u of gamma of ti, is plus infinity or minus infinity. So as soon as we see a plus infinity or minus infinity in any of them, we assign the value plus infinity to the whole left-hand side. We don't care if we're doing plus infinity minus plus infinity. Whatever happens, we just let that to be plus infinity, which forces for this to be true that the integral be infinity. And that is why we exclude non-constant curves. This is why we exclude, as is very conventional in all of this business, we exclude non-constant path. Path is just synonymous with curves, because if you have the same point, this integral has no chance to be non-zero, but this one under our convention can be infinity. So that's just technicality, not too much. After all, non-constant curves don't say much about the behavior of the function, so we exclude them. Okay, so let's look at our definition. Let's make sure everything makes sense. The reason why we require Borelness is because that is the condition that makes sure that we can define this. Remember, this is defined as integral from t1 to t2 of rho of gamma t dt. So we need this to be measurable, L1 measurable, and Borelness is a sufficient condition, not necessary, but a sufficient condition guaranteeing that along any continuous curve that you take, this rho composed with gamma is a measurable function, so that this Lebesgue integral will make sense. Well, yeah, so u is again understood. It's just a function and everything else. A very remarkable point here, something that we really should not take for granted, is that there is at this point no measure assumed on a metric space X. So this will change later. So we don't have any assumption of measurability of the function u or of the Borel function rho. Well, I mean, we assume it's Borel measurable, but not measurable with respect to any other measure. So this is a purely metric thing. So this definition only requires a space X and a distance, no measure yet. The notion of rectifiable curve and arc length parameterization makes sense in only metric space, and everything else here is just a metric thing. So keep that in mind, it's very important. So examples that we saw before and all the calculations we did is saying that if you take x to be R2, then gradient of u, absolute value, is an upper gradient of u for any C1 function u along any C1 path gamma. Because those were the assumptions to make those calculations work out. So upper gradient is a generalization of this notion of modulus of the upper gradient. Remember, it's just a modulus. It's a real positive valued function, so we lose all the information about the gradient. So if you are in Rn, gradient of u is is a vector space, a vector field. At every point it has a magnitude and a direction. With this absolute value, we throw away the direction, only keep the magnitude. This, of course, looking at loops, the end values difference will be always 0, but then this integral will rarely be actually 0 along the curve. So this will usually be non-zero, positive, but the inequality will also hold. In a general metric setting, of course, you don't expect anything like fundamental theorem of calculus so that you have equality here instead. That's just too much to ask. One silly reason is, suppose you have this curve, and this is the endpoints. You're saying that the u value here and difference with the u value here is bounded by integral along the curve. Now you can say, what if my curve, I do the same curve, except that I do twice this loop. So this side integral goes up while the u value difference is the same. So generally, you really have no hope of having equality. That's why upper gradient condition is an inequality. There is the next remark that any function does have an upper gradient along any curve, any path arc length parameterized curve. This may seem like I'm making a huge claim, a big, deep claim, but it's actually an artifact of the definition and how inclusive it was. You can allow rho to be just plus infinity because it is allowed by definition. And if you integrate along any non-constant path, you get infinity here, which is bigger than whatever happens on the other side. And this is actually not a bad thing because we love having non-empty sets. So the set of the collection of upper gradients of a function is non-empty. But of course, this is not an interesting one. This says nothing about how u changes along curves, and that's a pretty useless one. That's why the issue is finding better upper gradients.